Hello everyone, welcome. So in this presentation, we are trying to address the problem to alleviate the need of label data for source code model by proposing a novel technique called InferCode based on the self-supervised learning concept. To build big code learning model, usually we need a lot of data, especially label data. Label data means that it requires some human effort to assign label to a sample in the dataset, or using some heuristic to label the data. Usually such data contains a lot of noise because it's too huge. We usually don't use all of them, but we only use a subset of them for our own purpose. Even if we use such subsets, we usually annotate them first before building any models on top of it. For example, the code classification dataset is collected on an online website where the student can submit their solutions for grading, or the method name prediction data is collected on GitHub by using some heuristic, or the vulnerability detection dataset that contains manually labeled function collected from 4 large C language open source projects. So collecting such large amount of label data is tedious and requires expertise. That's why we propose to use self-supervised learning to alleviate the needs for label data. Right. So here are some examples of how self-supervised learning is applied in other domains. For example, in computer vision, usually we want to train a convolutional neural network model for vision learning tasks such as image recognition, object detection, and we will feed the CNN a lot of image with label such as dog, cat, car, or something like that. But in this case, we assume that we don't have that much label data. So how do we train a convolutional neural network? And the self-supervised learning method come to the rescue. So in this case, we will rotate the whole input image. Our goal is to predict which rotation is applied when rotating an input image into different angle. Once the model is converged, the parameter of the CNN is trained. So we can somehow train the CNN model without the need of label. Okay. So another self-supervised learning task for computer vision is to solve a jigsaw puzzle. So an image is cut into different patches, and the goal is to train the CNN model to organize the patches to form the original image, right? And those are some examples of how self-supervised learning is applied in computer vision. And how about in natural language processing, which is another domain? The first example of self-supervised learning is in natural language processing is Doc2Vec, which is quite a well-known model in NLP to learn the vector of document or paragraph, right? So the task here is to use the paragraph ID to predict which word is appear inside the paragraph, right? So another task is the masked language model that has been used in BERT, which is another well-known NLP model. The task is to randomly masking the word in a sentence, and the goal is to ask the model to train what is the missing word, right? Right. That's some example of how self-supervised learning for computer vision and natural language processing. How about self-supervised learning for big code? Unfortunately, little effort has been invested to design self-supervised learning model for source code, and most of the tasks are still based on a human annotated dataset. Right. There are some well-known models for code, but most of them does not focus on self-supervised learning. Okay. So our contribution in this work is to design a self-supervised learning model of code. The model is trained once on a self-supervised learning task and can be reused for other downstream tasks. And another benefit of our work is that the model is general for multiple programming languages. So here are a few key principles of self-supervised learning. Basically, the goal of training any neural network is to train an encoder such that the encoder can map a data representation to a vector v, right? Of course, it needs to be trained with an objective function. It can be the cross entropy function for a classification task, for example, and usually in the classification task, we need to feed the model with lots of human label data. In self-supervised learning, our goal is to design a new task to predict the pseudo label to train the model. So we need to find out how we can come out with such pseudo label data. For example, in vision learning, pseudo labels can be the rotation of an image, right? To summarize, Self-supervised learning is all about designing a new task with pseudo label to train the encoder, right? So we don't need to manually label the data to train the model, right? So what is the task in our InferCode? To give an intuition, we can start with a simple example. There are two bubble short programs here. Although they are written in different way, but there are still some similar part of the program, such as the initialization in the for loop and the assignment to swap the element of the array, right? So with such observation, so the question is that can we leverage such similar part in the program as the pseudo labels, right? Because they are similar. Of course, they should be closed in the vector space. That's our main intuition in InferCode, right? So the intuition. So this is our InferCode model. Each code element can be seen as a subtree and will be used as the pseudo label. So our model is inspired from word to vec. So we can see that each word in a document is used as the pseudo label. We use the document ID to predict each word inside such document, right? But in this case, we inspire from that, but we are not exactly the same. So in our case, we train the encoder to predict the subtrees. After train, the encoder can map any code snippet into a vector, right? And the code vectors of the code snippet with similar semantics will be closed in the vector space. Okay. So how do we extract the subtree? So basically, we have a very high level idea is that we traverse the tree and we only choose the 5 grand subtree and ignore the large one, because the large one is very unique for different programs, right? So we don't want to. So it's very unique. It doesn't bring much value in the training process. Okay. So for the evaluation protocol, there are two phases: training and evaluation. For training, first we train the encoder with a large dataset to predict the subtrees. For evaluation, for different tasks, we use the dataset collected specifically for such tasks, fit into the pre-trained encoder to get a vector and use the code vector to do something. Or we can use such dataset to fine-tune the pre-trained encoder to achieve better results for some other tasks. Okay. So which means that there are two main ways to use the pre-trained InferCode model. The first way is to use the code vector produced by the encoder for downstream tasks, which are code clustering, code clone detection, and code-to-code shot for cross-language. And the second way is to fine-tune the pre-trained encoder for downstream tasks, such as so we choose code classification and method name prediction in the second way. So due to the limitation of time, I will just show the evaluation result directly. More details can be checked directly in our paper. We present the result of code clustering, cross-language code shot, and code clone detection as a demonstration of the usage of code vector produced by the pre-trained encoder. So the results show that InferCode outperforms most of the state-of-the-art baseline for each of the tasks, as we can see here. More detail and you can check in the paper. So for fine-tuning the pre-trained model, we apply into code classification and method name prediction. We split the data for fine-tuning by X%, where X can be 1, 10, or 100%. We can see that for either task, where when X is equal to 100, the fine-tuning results are better than training the model from scratch. So we can see here the results here are better than the result in the supervised training model, right? So here we did some analysis to analyze how good the vector produced by different code embedding techniques. We can see that from the visualization, the embeddings of similar programs produced by InferCode are well grouped into clusters, which means the boundary between clusters are clearer than the two other techniques, as we can see in the tree visualization here. Okay. So this is the summary of our paper. So first, our model is inspired from the doc2vec. Second, to extract the subtree, we only choose the 5 grand subtree and ignore the large one. Thirdly, is that we have two ways to use the model. The first one is to use the code vector produced by the encoder, and the second way is to fine-tuning the pre-trained encoder for downstream tasks. And for evaluation, we train the model on a very large data set, and we use it for an evaluation data set for different tasks. Okay. So thank you, and thanks for listening. Hope you will enjoy our presentation.
Okay. Good morning to everybody. You have seen a pre-recorded video by New Bai. New Bai work at the Huawei Research Island, and when he wrote this paper was from Singapore Management University. The paper is a technical paper. What can I say more? Nothing else. So if you have some question, is there some question from the audience? Please write that question in the chat. There are no questions. There is an icebreaker in the audience. No icebreakers? Okay.
Yeah.
Don't worry. I'll play the role of icebreaker, hoping that after my question, a lot of attendees will formulate some question for me.
Yeah.
First of all, I have appreciated the fact that you have made available InferCode on GitHub. Let me formulate my first question. InferCode uses a tree-based convolutional neural network to build a pre-trained model. You try to apply this model to downstream unsupervised tasks such as code clustering, code clone detection, and cross-language code search.
Yeah.
Experimental results show that you got appreciable results on all these kind of applications. On the basis of your experience, what is the kind of application of InferCode more promising? For example, on code clone detection or cross-language code search. And if you can do such a kind of postulation, can you explain why your approach is more promising on such a kind of application?
I think instead of saying my approach is more promising the other work for this kind of application, we say I would say my approach has an advance than the other because they need label to train the model with label. Need the label. Although on some aspect we may not be better than them on some aspect, but we don't need label. They need a lot of label. So comparing to the two approaches, they need a lot of label to train the model. Larger data set, we need a smaller data set, right? Smaller data set, noisy data set to train the model, and we can get very close performance to them. I think that's the strong aspect of our approach. Instead of saying we keep training the model, designing a new model that can beat them in some metric, that's not the goal in our work. You got the answer?
I had a little technical problem that I've solved a short time. So we have a question from the audience. So these sound good for us. Can you share your opinion of language scalability? For example, what if using this approach for scripting language or functional language rules, IST can be a little different? This question is from Zhu Wenqing.
That one of my author, Prof. Yijun, has helped me to answer. Yeah, as the answer stated, we used the parser that can parse different programming languages. For now, we are using tree-sitter, which is a parser. I mean, a parser that can parse multiple languages, programming languages, and scripting languages such as JavaScript, Scala, Haskell, and many more. So because we build the model based, so we are not limited by any programming languages.
Okay,
Yeah.
we have also another question from the audience. It's more or less related to past research on the field, on the research field that you have approached in your research. In particular, the question is, can you explain how InferCode model is different from IBM project CodeNet mentioned in a keynote early?
Yeah. The project CodeNet mentioned in the keynote basically is a data set. It's not really the model. So I think InferCode can apply to train on the project CodeNet data. Yeah, that's basically the difference. We are a model. We can train on any data set, while the project CodeNet is basically a data set, a large data set for multiple purpose.
Can you elaborate more? Because I think that it is not completely clear what is the difference between InferCode
So
and...
the difference is that InferCode is a model, while the project CodeNet is basically a data set. So so we can also apply InferCode to train the data set released by the project CodeNet.
So
The project is not a model.
If I well understood, you are saying that InferCode is a model, while the project CodeNet by IBM is a dataset. So in the future,
it's a multiple data set together. They call it they collected and they call it the project CodeNet. They did not really propose a new model. It just collect the data set. That's what I know from them.
Okay. We have about 3 minutes, and it seems that we don't have any question from the audience, so I have prepared one question for you.
Yeah.
My question is the possible practical implication for the research presented in your paper are mostly obvious, but I would like to ask you if you can provide some consideration on the implication from the software practitioner point of view. So what is the practical implication for the results you have achieved in your research? Given also that you're moving to UAV research, so I think that there are a lot of actionable results that can be used in industry, in the software industry. Can you explain, can you provide us some hints, some intuition about that?
I think, thanks for the question. I think from the software practitioner perspective, InferCode can be useful in many applications, such as they want to analyze they want to visualize how different code fragment of the project looks like. For example, for each of the file, for each of the function of a whole big project, they can convert each of the file or each of the function into a vector. Then you can visualize the vector to see for example, the clones, right? For example, or you can cluster multiple parts of the same program together to see how to analyze the function of your programs. Because when you convert into the vector, it's very easy to visualize all of them into something that you can see. Right? Yeah, that's I mean to apply InferCode, code clone detection, code clustering. You can see how how your code looks like from the vector perspective.
Okay, thank you for the answer. We have 30 minutes, I'm sorry, 30 seconds. So I have just a quick question for you and concern external validity of the experimental part of your piece of research work. And the question is, to what extent do you believe that observed results can be generalized? You have less than 20 seconds to answer.
Okay. So to improve the model, I think there can be many possible ways. One way is that we can replace the encoder, the tree-based convolutional encoder that we have